So what we're going to do today is we're going to work through the new chapter 19. The old chapter 19 was about vector spaces, but the new chapter 19 is about extension fields. This is a pretty tough subject. Let's work through this together. This was definitely a subject that gave me a lot of trouble in grad school, to tell you the truth. We have in grad school for math these what they call written prelim exams. And one of them was about abstract algebra, and the group theory and the ring theory stuff I did okay on, but the field theory stuff, especially extension fields and everything that follows from that, I really had a lot of trouble with. And I only had success once I realized that examples really help, for one thing. And even doing calculations that might seem like, well, that's high school math, like long division or synthetic division, helps a lot as well, especially if you maybe do it mod P. So let's work through this. First, we have this definition. A field E is an extension field of a field F if, well, first of all, F is a subset of E. E is the bigger field, E is the extension field. And the operations of F, the smaller field, are those of E restricted to F. Kind of a convoluted definition. This is equivalent to F being a subfield of E. So why have a different definition? Usually, when we talked about subgroups and subrings and subfields before, we had a big group or a big ring or a big field to start off with. And we were interested in, well, breaking it down to smaller pieces. Understand the whole, by understanding the pieces is kind of the overall philosophy there. Here, in going more in depth into field theory and these extension fields, we have a different purpose. We've got a field that in some ways you might call it's defective. We can't factor our polynomial over this field, for example. It might be irreducible. So the question is, can we make a bigger field, an extension field that does contain the roots of the polynomial? It does allow us to factor the polynomial. And that's what we do. Why? For what purpose? Ultimately, you can do things like prove that the complex number field contains all roots to all ordinary polynomial equations that you can come up with. That's called the fundamental theorem of algebra. That's one thing you can do. You can do other things. You can prove, for example, that quintic equations, 5th degree and higher, are not solvable by radicals. And what that means is there's no analog of the quadratic formula for 5th degree and higher. There actually is for 3rd degree and 4th degree, though they are very, very complicated formulas. But once you get to 5th degree and higher, there's no formula. That takes proof. Proof's very hard, but it was a great success in math to eventually come up with that proof. And that's part of what all of this theoretical stuff we're going to get into is about, is proving that, though we don't get to the actual proof of that. Anyway, that's just to give you a big picture of what's going on here. Cauchy observed in 1847 that this thing is a field that contains a zero of x squared plus 1. What a weird thing to say. Wait, is that a field? Think about this with me here. R, the real numbers, that's a field, right? The field of real numbers. But Rx, that's not a field. I've emphasized that before. Rx, the ring of polynomials with coefficients from the real numbers, or the coefficients from any field, itself is not a field. Why? Because any non-constant polynomial is not going to have a multiplicative inverse, will not be a unit. Constant polynomials that are non-zero will. 5, for example, will have an inverse 1/5 as a polynomial in there. But any polynomial that has degree 1 or higher, it's not constant, won't have an inverse, like x. X doesn't have an inverse in there. It does have an inverse in a bigger field, the field of rational functions. It would be 1 over x. But we're not talking about that field. It doesn't have an inverse in R of x. But, wait, this is a field. What is this? This is a factor ring where we are modding by an ideal, a principal ideal generated by x squared plus 1. The claim is Cauchy observed that this is a field. Well, why is it a field? It turns out to be a field because x squared plus 1 is irreducible over R, right? There's some theorems. If x squared plus 1 is irreducible, this ideal will be a maximal ideal. And am I making connections in your brain here? That's a maximal ideal, which makes this a field. We had some theorems back in chapter 14, for example, that allowed us to prove that. Why does it contain a 0 of x squared plus 1? Why does that thing, which is a field, contain a 0 of x squared plus 1? It doesn't seem like it would. What do the elements of that look like? Okay, Rx, polynomial ring with coefficients from R, form the factor ring where you mod by the ideal generated by x squared plus 1. That is a field. What do its elements look like? Well, they are cosets, right? This is a factor ring. The elements have to be cosets. Technically, you could write in the abstract, they are all cosets of the form f of x plus the ideal, where f of x varies over Rx. But we have seen, somewhat amazingly here, this is, you might call it amazing, that we can actually simplify the coset representatives to being just linear polynomials. Ax plus b plus the ideal. Of course, the question is why? Why can we do that? But why? That's related to coset properties. X squared plus 1 plus the ideal. The x squared plus 1 is an element of the ideal. It gets sucked into it. Giant slurping sound. You can say it is the ideal itself, effectively. Or the 0 element. You could write this as 0 plus the ideal. The additive identity in the factor ring, which is a field. And because of that, that's equivalent to saying, by subtracting 1 from both sides effectively, that x squared plus the ideal is -1 plus the ideal. And what that ends up meaning is, in considering examples of cosets, if you've got a degree 2 or higher, you can always simplify it to a lower degree. As an example, x to the 4th plus x cubed plus x squared plus the ideal. The x squared can get replaced with -1. The x cubed can get replaced with -x. And the x to the 4th can get replaced with, well, -1 squared. Here's the details. Think of it this way. Replace all these x squareds with -1s. Why? It's allowed by that fact there. -1 squared is +1. X times -1 is -x, and that's a -1. And then the ones cancel. This simplifies to -x plus the ideal. A linear polynomial representative. But getting back to what the book claims that this field has, well, x squared plus 1 has a root in this field. What? Somewhere, one of these cosets evidently is a root of x squared plus 1. What is it? How in the world, what? How could that be the case? What's the root? I don't see any, for example, i's in there where I squared is -1. You know, I, the complex imaginary unit, is a root of x squared plus 1, a 0. But I don't see any i's in here, unless I called one of these letters I, but that would feel kind of phony, because I is supposed to be the imaginary unit. Okay, it's a little bit of experimentation to realize it. But the root, well, let's give it a name, turns out to be, let's call it alpha. Let alpha equal x plus the coset, or x plus the ideal. That coset. So alpha is here one letter symbol for the entire coset, just for sake of convenience, just for the sake of emphasis. What happens if I square alpha and add 1 to it? And well, what would this 1 be? Is there a 1 in this ring? Yes, as long as you realize this is the 1 in this factor ring, the unity, which means it itself is a coset, though it doesn't look like a coset, does it? What is alpha? Alpha is this coset, x plus the ideal. I'm squaring that and adding the unity coset to it, which is 1 plus the ideal. What happens when I do this? When I do these coset calculations? I'm squaring this coset, which means I square its representative. And get this coset. And here, well, this coset is just itself. And now I'm adding cosets. This coset plus this coset. You add cosets by adding representatives. I use parentheses there. I didn't have to, but just a little for emphasis. And then giant slurping sound that gets sucked in there. In other words, this is the identity coset, additive identity. Quote unquote equals 0, where big 0 represents the 0 coset of the factor ring, which is a field. Whoa. What have I just done? This is in the field here where that is defined as a factor ring. What have I just done? I have just verified that this element, which is a coset, has the property that when you square it and add the unity, you get 0. It's a root of x squared plus 1, in other words. The polynomial x squared plus 1, where 1 is, well, it's the unity of this, but it is still a 1. Weird, but true. And there's no need to introduce the imaginary unit I. Is there any way to relate this to imaginary numbers, though? Imaginary and complex numbers. In fact, if you look in the paragraph above, it says this is a field isomorphic to the complex numbers. Really? These cosets could be thought of as complex numbers or something? Yeah, I'm not going to go through all the details, but if you're going to prove it, the way you'd prove that is you'd have to come up with well, you'd want to use the first isomorphism theorem for rings. And you come up with a homomorphism from Rx to C that has what? That's onto, first of all, and it's got this ideal as its kernel. Then you'd be able to apply the first isomorphism theorem. How can you possibly come up with a homomorphism that has this ideal as its kernel? Map any polynomial in Rx to its value at the imaginary unit I, pretending you know what the imaginary unit I is, assuming that. That is going to map x squared plus 1 to I squared plus 1, which by definition of the imaginary unit I is 0. And any polynomial multiple of x squared plus 1 will also get mapped to 0. That means the kernel, that's enough to imply the kernel of phi is the ideal generated by x squared plus 1, and then apply the first isomorphism theorem. to verify it's onto as well, but that's not too difficult. Give me any complex number, find a polynomial that gets mapped to it. Actually, you could, yeah, it's possible to verify. I won't go through the details. Yeah, a plus bx would get mapped to the complex number a plus bi. A polynomial a plus bx would get mapped to the complex number a plus bi. That would be enough to verify it's onto. All these things are related. Okay, let's continue. The fundamental theorem of field theory, Kronecker's theorem, generalizes what we just did. Let f be a field, let f of x be a non-constant polynomial with coefficients from capital F. Then there exists an extension field, E of f, in which f of x has a 0. This thing here could be thought of as an extension field of R, it turns out. And the proof of this essentially generalizes what we just did with the example. I won't go through it, but ultimately here you end up plugging in the coset x plus the ideal, and that's your root, that's your f. So it's very similar to what we just did, just more abstract. Let's look at example 2 next. We are going to be continuing to work with finite fields. The simplest finite fields are ZP, where P is a prime, but there are going to be other finite fields that are not isomorphic to ZP. But ZP certainly is the simplest. To get ourselves warmed up toward further examples, let's look at example 2. Let f of x be this quintic, this 5th degree polynomial with coefficients from Z3. So all the coefficients are 0, 1, or 2. You can factor this polynomial over Z3. Okay, now, first of all, when you read this, realize that if you were asked to factor this, probably it would be very difficult. It's not obvious that this is how to factor it right away. Though, once you see the factorization, you should be able to check it. Let's go ahead and do that by multiplication. So, I'm not ruling out on the final exam, just having you check things by doing arithmetic effectively. Multiply these polynomials in this ring, that's going to mean you need to multiply them in the ordinary way, but then mod the coefficients by 3 in this case. Not the powers, but the coefficients. So I'll multiply x squared first by every term over here to get x to the 5th plus 2x cubed plus 2x squared. That's multiplying x squared times every term over there. Then I'll multiply 1 times every term, but the answer is maybe underneath here. 1 times x cubed is x cubed. 1 times 2x is 2x, and then 1 times 2 is 2. Add like terms. I'll go ahead and write plus 3x cubed, but because we're doing mod 3 arithmetic, that's going to become 0x cubed. The x cubed term is going to go away. So I'll write it, but then I'll get rid of it. X to the 5th plus 2x squared plus 2x plus 2. We're doing the calculation mod 3 there for the coefficient. And compare what's in the book. And you see we did verify that we get this 5th degree polynomial. It says it's an irreducible factorization. That must mean that both of those are irreducible. Actually, you should have been able to prove that kind of thing with the last exam. Think back to chapter 17. Think mod P irreducibility test. Well, actually, you don't need that because we're not talking about irreducibility over Q. Instead, just realize, hey, that has degree 2. It's good enough to check that it has no zeros in Z3. Yeah, the only possible zeros are 0, 1, and 2. And none of those work, right? 0 squared plus 1 is not 0. 1 squared plus 1 is 2, not 0. 2 squared plus 1 is 5. Mod 3 is 2, not 0. So this is irreducible over Z3. That also has degree 2 or 3. So the same thing would work there. Check that neither 0, 1, or 2 are zeros of this. That would say this cubic is also irreducible over Z3. That's an irreducible factorization, but neither of those has a 0 in Z3. So we can't factor it anymore into linear factors over Z3. But can we find an extension field, E of Z3, in which this polynomial does have at least one zero? So Z3 is kind of a small field, just 3 elements. That's your F. You're trying to find an extension field in E that's bigger, in which this polynomial does have zeros. We're hoping that we can generalize such examples to prove powerful things about solving polynomial equations. But we need to work with the examples first. What does the book say works? Actually, the book gives you 2 examples that work. You could take E to be this factor ring or this factor ring. What in the world do they do there? Well, remember the polynomial, this is the f of x here. It's got this factorization. One factor is x squared plus 1. The other factor is x cubed plus 2x plus 2. Both of those are irreducible over Z3. Therefore, we know from theory that both of these ideals are maximal in Z3x. Remember, Z3 is a field. I get 3 elements. Z3x is not a field. That's a polynomial ring. And any non-constant polynomial doesn't have an inverse in it, but these ideals are maximal because the polynomials that generate them are irreducible over Z3. Therefore, when you form the factor rings, these are fields. The claim is this is a field with 9 elements, and this is a field with 27 elements. These are extension fields of Z3. That's not obvious, perhaps. We'll try to figure out why that's true. And maybe what the book is hinting is these both have roots of the polynomial. I bet x plus the ideal, just like the example from 10 minutes ago, that probably works. Very important what I'm saying here. But why is this a field with 9 elements? We're just wrestling with the reading here. Z3x, polynomial ring, coefficients from Z3 mod by this principal ideal that is also a maximal ideal. Why does that have 9 elements? Just like with the example Rx mod this kind of ideal, you can simplify the Coset representatives to being linear. Ax plus b plus the ideal. But now the a and b are not arbitrary real numbers. They are elements of Z3. So there's 3 choices for a and 3 choices for b. 3 squared equals 9 choices total. This has got 9 elements. This kind of thing came up on the last exam as well, but I'm re-emphasizing. And yeah, the coset x plus the ideal is a root of the polynomial x squared plus 1. It's a little weird. I'm kind of using the x's in different ways here. This is a coset in this factor ring. This is just sort of an arbitrary polynomial. And I'm saying if I plug this coset into that polynomial in place of x, just like I did with the example 10 minutes ago, it'll be a root. Why is this an extension field of Z3? Is there a subfield of this that's isomorphic to Z3? Let the a be 0. Consider all cosets whose representative is just a constant, B, that's 0, 1, or 2. And that'll be a subfield of this isomorphic to Z3. Therefore, this can be thought of as an extension field of Z3. You might wonder, if that's a root of the polynomial x squared plus 1, and x squared plus 1 is quadratic, can I find another root of it? If I call this alpha, could I find another root of it? Yeah, negative alpha works. But what's negative alpha? It's that. But what's that? Bring the negative sign through in front in terms of the Coset representative. You can keep the ideal as is. It's that, but we should really mod the coefficient by 3. What's negative 1 mod 3? It's 2. This is another root of x squared plus 1. I'm using the word root. The book usually uses the word 0, but they're basically synonymous. Roots and zeros of polynomials, those words mean the same thing. Really? What would happen if I plug in this polynomial into x squared, this coset into x squared plus 1? Meaning square it and add 1, where 1 is the unity coset. Here I'm plugging this coset, 2x plus the ideal, which is the additive inverse of this coset, x plus the ideal, into the polynomial x squared plus 1. So I've got to square the coset and then add the unity. Thinking about coset operations, this gives 4x squared plus the ideal plus the unity. But I need to mod 4 by 3. I am doing coset simplification mod 3 still. So 4 reduces to 1. Mod 3. That's mod 3. And then add those cosets. And once again, we can finish it with a giant sucking sound. That gets sucked in. This is the identity coset. That is the 0. Make it a big 0. These calculations, yes, they're weird. But this is ultimately supposed to be the fun part. When you get enough practice with these things, you start to get good at them. This is supposed to be like the fun part. The not so fun part maybe is the theorems and their proofs. The examples are meant to be the fun part. Though the theorems are still relevant because they help you understand what's going on, or you can interpret what they mean in terms of examples at least. We also could take this to be an extension field, and it's got 27 elements. Why does that have 27 elements? So I'm taking that polynomial ring Z3x again and multiplying by another modding by another maximal ideal, forming a factor ring by another maximal ideal because x cubed plus 2x plus 2 is irreducible over Z3. And therefore, this must be not just a ring, but a field. Why does it have 27 elements? So we're talking about here now Z3x mod the maximal ideal generated by x cubed plus 2x plus 2. What do the elements of that look like? They are cosets once again. But now it turns out, without explanation here at first, that because this irreducible polynomial is cubic, that you need quadratic representatives for the cosets. Say ax squared plus bx plus c plus the ideal as A, B, and C vary over Z3. A, B, and C vary over Z3. So you got 3 choices for A, 3 choices for B, 3 choices for C, altogether 3 cubed 27 elements in this field. Do you notice with these examples, field of 9 elements and a field of 27 elements, the number of elements is a power of a prime. We will see here next Monday probably that all finite fields have order equal to a power of a prime. There's no finite field, for example, of order 6, 2 times 3. There's no finite field of order 10, 2 times 5. There is a field of order 2, Z2, and order 4, 4 squared, or 2 squared, and order 8, order 16, order 32, powers of 2. There's also a field of order 3, 9, 27, 81, 243, powers of 3. 5, 25, 125, 625, etc., powers of 5. Why is this true? Why can you write the Coset representatives as quadratics? Effectively, it's related to the fact that, well, x cubed plus 2x plus 2 plus the ideal is in fact the 0 element of the factor ring, right? That gets sucked in. And that's equivalent to, if you subtract 2x from both sides and subtract 2 from both sides, it's equivalent to saying x cubed plus the ideal is, you could write it as minus 2x minus 2 plus the ideal, or modding negative 2 by 3. Negative 2x is the same as positive x, and negative 2 is the same as positive 1. So anytime, this is mod 3 here, anytime you see an x cubed in calculations with the cosets, you can replace it with x plus 1. For example, if you had x to the 4th plus x cubed, you could write that as x times x cubed plus x cubed. You could replace each x cubed with x plus 1 in this factor ring, which is a field. Effectively, I am doing coset calculations here without writing the ideal when I write this kind of stuff. So this simplifies to x squared plus x is 2x plus 1. You could replace x to the 4th plus x cubed with that in this factor ring, which is a field. Again, and the author emphasizes this, when I write this kind of thing, I'm really doing coset calculations without bothering to write the plus, the ideal. Because it's just sort of a placeholder anyway, in a sense. So why bother is kind of the philosophy there. This is calculations in this factor ring, which is a field, without writing the ideal. Without ideal. I'm being a little sloppy, you might say. In each case, I could bring the ideal down there.